Picture this: a star, not so different from our own sun, shining brightly in the darkness. But this star isn't anchored to a bustling galaxy, surrounded by siblings in a cosmic family. No, this star is utterly alone, adrift in the infinite void between galaxies, a solitary wanderer in the coldest, emptiest reaches of space. How did it end up here? What happens to a star when its home galaxy is torn apart by collisions or slowly unraveled by the universe's expansion? These are the galactic orphans, stars abandoned by the very systems that gave them birth, left to fend for themselves in the unforgiving cosmos. And their stories are some of the most haunting and revealing tales the universe has to tell. Think about the sheer scale of that isolation. Galaxies are like bustling cities, teeming with stars, gas, and dust, all bound together by gravity's invisible hand. But when galaxies collide or disintegrate, some stars are flung out into the void, ejected from their homes with no way back. It's as if you were suddenly ripped from your neighborhood and thrown into the middle of an endless desert, with no landmarks, no companions, just silence and emptiness stretching in every direction. Yet these stars don't just fade away. Some burn on for billions of years, their light a faint beacon in the dark. Others meet more dramatic fates, collapsing into black holes or exploding in brilliant supernova, their deaths echoing across the cosmic wilderness. What makes these galactic orphans so fascinating isn't just their solitude, it's what they reveal about the universe itself. Their journeys map the hidden forces shaping the cosmos, from the gravitational tides that tear galaxies apart to the dark matter that guides their paths. By studying these wanderers, astronomers can piece together the history of galactic collisions, the life cycles of stars, and even the fate of our own Milky Way, which will one day merge with its neighbors, scattering stars of its own into the void. So join us as we follow these cosmic outcasts, tracing their paths through the darkness and uncovering the secrets they hold about the universe's grand, ever-changing tapestry. This is the story of the stars that no one wanted and the profound truths they carry with them into the endless night. Stars begin their lives cradled in the swirling arms of galaxies, where dense clouds of gas and dust collapse under gravity's pull, igniting the nuclear fires that will sustain them for millions or even billions of years. These stellar nurseries are vibrant, crowded places. Imagine a cosmic metropolis where stars are born by the thousands, clustered together in glowing neighborhoods. But not all stars get to live out their lives in these bustling communities. Some are violently uprooted, torn from their galactic homes by forces far beyond their control. The most dramatic way a star becomes an orphan is during a galactic collision. When two galaxies crash into one another, their gravitational fields twist and warp like invisible tidal forces, flinging stars out into the void like sparks from a fire. These interactions aren't slow or gentle, they're chaotic, explosive events that can hurl stars at incredible speeds, sending them careening into the emptiness between galaxies. It's like a cosmic game of pinball where stars are the balls and gravity is the flipper, launching them into the abyss. But collisions aren't the only way stars lose their homes. Sometimes galaxies simply unravel over time. As they rotate, their outer edges can stretch thin, and stars on the fringes may slip free, drifting away like boats untied from a dock. Other times, the gravitational tug of war between a galaxy and its neighbors can pluck stars loose, sending them spiraling into the void. Even supermassive black holes at the centers of galaxies can act like cosmic catapults, flinging stars outward with unimaginable force. What's astonishing is how these orphaned stars endure. Unlike planets which would freeze and darken without a sun to warm them, these exiled stars continue burning, their light undimmed by their solitude. They carry on, some for billions of years, traveling through the coldest, emptiest regions of space with nothing but their own glow to keep them company. And yet, their very existence tells us something profound about the violence of galactic evolution, the resilience of stars, and the unseen forces that shape the universe. Every orphaned star is a witness to cosmic history, a silent traveler with a story etched in its light. Just as no two snowflakes are alike in a winter storm, orphaned stars come in all shapes and sizes, each with its own fate written in starlight. Take the massive blue giants, for instance. These are the rock stars of the cosmos, dazzling but short-lived. Born with several times the mass of our sun, they burn through their nuclear fuel at a breakneck pace, shining with an intense blue-white glare that can outshine entire galaxies. But when they're flung into the void, their brilliance becomes a lonely beacon. Without the shelter of a galactic neighborhood, these giants meet explosive ends, collapsing into neutron stars or black holes in spectacular supernovae that briefly illuminate the darkness like cosmic fireworks. Then there are the red dwarfs, the quiet survivors. These small, cool stars might not command attention like their blue cousins, but they are built for endurance. With only a fraction of the sun's mass, they sip their hydrogen fuel slowly, stretching their lifespans into trillions of years. For a red dwarf cast adrift, isolation is just another chapter in an unimaginably long life. They glow faintly like embers in a dying fire, outlasting entire eras of cosmic history. Some may even outlive the galaxies that once birthed them, becoming the last stars shining in a cold, dark universe. But not all galactic orphans are stars at all. Rogue planets' worlds torn from their solar systems drift through the void like ghost ships. These frozen nomads, once warmed by the light of their parent stars, now wander in perpetual twilight. Without a sun to sustain them, their atmospheres freeze solid, their surfaces scoured by cosmic radiation. Yet even here, there's a glimmer of possibility. Deep beneath their icy crusts, tidal forces or radioactive decay might maintain hidden oceans, pockets of liquid water where life, against all odds, could cling to existence. What determines an orphan's fate? Mass is the great divider. Heavier stars live fast and die young, while lighter ones fade slowly into the night. Composition matters too. Stars rich in heavier elements might forge new worlds even in exile, their debris coalescing into planets around them. And then there's velocity. A star flung outward at tremendous speed could cross the intergalactic void entirely, destined for a lonely journey between galaxy clusters. Others, moving more slowly, might linger on the fringes of their former homes, caught in the gravitational backwater of galactic tides. These cosmic outcasts are more than just celestial curiosities. They're time capsules, preserving the conditions of their birth galaxies long after those systems have changed or vanished. A blue giant's explosive death seeds the void with heavy elements, future building blocks for new stars and planets. A red dwarf's steady glow could one day nurture life on a rogue planet warmed by its faint light. Even the darkest, coldest wanderers hold clues about the violence of galactic evolution, the resilience of matter, and the untold stories written in the spaces between the stars. The journey of a star from the heart of a galaxy to the emptiness between them is a story written in the language of gravity. To understand how a star gets kicked out, we have to picture the invisible forces at play, forces so powerful they can hurl an object millions of times more massive than our entire solar system into the void. One of the most common ways this happens is during galactic collisions. When two galaxies spiral toward each other, their gravity doesn't just pull them together. It twists and warps their structures, flinging stars out like stones from a slingshot. Imagine two vast crowds merging, and in the chaos, a few individuals get shoved so hard they're sent flying out of the group entirely. That's essentially what happens to stars caught in the gravitational crossfire. But collisions aren't the only way. Sometimes a star gets too close to a supermassive black hole lurking at the center of its galaxy. These black holes are like cosmic wrecking balls with gravity so intense they can bend space itself. If a star swings near one in just the right way, it can be catapulted outward at incredible speeds, a phenomenon called the slingshot effect. Think of it like a gravitational assist where the star steals a bit of the black hole's energy to propel itself free. Astronomers have even detected hypervelocity stars racing through space at over 1 million miles per hour, their speed a telltale sign of a black hole's violent handiwork. Then there's the slower, quieter method, galactic evaporation. Over billions of years, stars on the outer edges of a galaxy can gradually drift away, tugged by the gravity of neighboring galaxies or dark matter halos. It's a gentler exile, like a leaf floating away on a river's current. But no matter how a star gets ejected, one thing remains the same. Once it crosses the threshold of escape velocity, there's no coming back. The galaxy's gravity can no longer reel it in, and the star becomes a true cosmic drifter, destined to wander the void until its light finally flickers out. What's remarkable is how these ejection events leave fingerprints. The speed, trajectory, and even the composition of an orphan star can reveal its origins. A star rich in heavy elements might hint at a violent past near a supernova, while one moving at extreme velocities points to a close encounter with a black hole. By studying these exiles, astronomers can reconstruct the hidden dynamics of galaxies, the collisions, the near misses, and the gravitational tugs of war that shape the universe. Every orphaned star is a messenger carrying secrets of the forces that govern the cosmos. Not all stars drifting alone in the cosmos share the same backstory. Some were outcasts from the very beginning, while others lost their homes after lifetimes spent in galactic communities. The difference between rogue stars and galactic orphans comes down to timing when they were ejected and what forces sent them spiraling into the void. Rogue stars are the rebels of the stellar world, flung out of their birth clusters while they're still young. Picture a stellar nursery where hundreds of stars form close together in a dense, turbulent cloud of gas. In these crowded conditions, gravitational tugs of war can send a star hurtling away at incredible speeds, like a marble launched from a slingshot. These runaways don't just drift, they race through space, often leaving their siblings far behind. Some rogue stars move so fast they're practically bullet-shaped, their fronts compressed by the sheer force of their motion through interstellar gas. These early ejections mean rogue stars spend nearly their entire lives in isolation, blazing a solitary trail through the galaxy. Galactic orphans, on the other hand, knew the comfort of a galactic home before being torn away. They weren't cast out in their youth, they were wrenched from mature star systems, often by the violent forces of galaxy collisions or the gravitational pull of supermassive black holes. Unlike rogue stars, which typically stay within their home galaxy, galactic orphans are exiled entirely, banished to the desolate stretches between galaxies. Their isolation is more profound, their journeys longer. While a rogue star might still pass by other stars occasionally, a true galactic orphan may travel for millions of years without encountering another soul. The distinction matters because it shapes how these stars live and die. A rogue star ejected early might still have protoplanetary material swirling around it, potentially forming planets even in exile. A galactic orphan, older and farther from any source of new material, is less likely to have companions, and when their time comes, their deaths unfold differently too. A massive rogue star might explode as a supernova within the galaxy, its light blending with countless others, but a galactic orphan's final moments would blaze alone in the darkness, a single, brilliant flare in an otherwise empty sky. Yet both types of wanderers teach us something vital about the universe. Rogue stars reveal the chaotic turbulence of stellar nurseries, while galactic orphans map the invisible forces that reshape galaxies over eons. Together, they remind us that even in the vastness of space, no star's journey is ever truly ordinary, and every exile has a story to tell. Once a star is cast adrift, it enters a realm of extremes, a place where the rules of survival are rewritten. The intergalactic void isn't just empty space. It's a near-perfect vacuum, colder and more desolate than anything within a galaxy. Here, temperatures plummet to just a few degrees above absolute zero, and the density of gas is so low that a star might travel for millennia without encountering a single atom. Yet against all odds, many of these exiles persist, their nuclear furnaces still burning bright. How it all comes down to what they're made of and how much fuel they carried when they were torn away. Take a star like our Sun, for example. If it were ejected into the void, it would continue shining much as it does now, steadily converting hydrogen into helium for billions of years. The absence of a galactic environment wouldn't extinguish it. Stars generate their own energy after all. But without the gentle stirring of nearby supernova or the gravitational nudge of passing stars, its eventual fate would be different. In a galaxy, an aging star like the Sun might one day be replenished with fresh gas, or its outer layers might mingle with neighboring nebulae. In exile, it would simply burn until its fuel ran out, then slowly shrink into a white dwarf, cooling over eons into a dark, crystalline relic. But not all stars fade quietly. Massive stars, those born with 8 times the Sun's mass or more, face a far more dramatic end. In a galaxy, their deaths are spectacular events, lighting up the cosmos with supernova that seed space with heavy elements. In the void, their explosions would be no less violent but far more isolated. A lone supernova in the intergalactic darkness would briefly outshine 1,000 galaxies, its light traveling unimpeded for millions of years before reaching another star system. The remnants, a neutron star or black hole, would then drift forever, invisible against the endless night. Then there are the true survivors, red dwarfs. These small, dim stars are the ultimate endurance athletes of the cosmos, with lifespans stretching into trillions of years. Ejected into the void, a red dwarf would continue its slow, steady burn long after other stars had flickered out. Its faint glow might one day be the only light in a universe grown cold and dark, a final beacon in an era when galaxies themselves have faded. But survival isn't just about time. It's about transformation. Some orphan stars, particularly those rich in heavy elements, might forge new worlds even in exile. Planets could coalesce from the debris of their formation, orbiting in perpetual twilight. Others might pass through rare pockets of intergalactic gas, briefly flaring to life as they accrete new fuel. And then there are the dark, frozen remnant stars that cooled into black dwarfs or neutron stars. Their heat radiated away over eons until they become little more than ghostly shadows against the cosmic microwave background. What's haunting is how few of these stories we'll ever witness. The lifetimes of stars dwarf human history, and their journeys through the void unfold on scales we can scarcely comprehend. Yet each one carries a record of its origins in its light, its motion, even its chemistry. By studying these wanderers, we glimpse not just their fates, but the fate of all things. For in the end, even galaxies are temporary. Stars born today will one day be orphans, and the void will claim them all. There exists a realm of isolation so profound it defies human comprehension, a star drifting not just beyond the edges of its galaxy, but so far into the void that the nearest galaxy is a faint smudge barely visible in its night sky. These are the loneliest stars in the universe, cosmic castaways adrift in a darkness so absolute it redefines solitude. Imagine standing on a planet orbiting one of these exiles. Look up, and instead of a sky glittering with the light of neighboring stars, you'd see almost nothing. A handful of distant galaxies might appear as pale, ghostly spirals, their collective glow weaker than a single star in our own Milky Way. The rest would be endless black, an emptiness stretching across billions of light years. The distances these stars traverse are staggering. While most galactic orphans remain within the faint gravitational halo of their former homes, some are flung so violently during collisions or black hole encounters that they escape entirely, hurled into the intergalactic wilderness at speeds exceeding 1,000 kilometers per second. At that rate, a star could cross the distance between the Milky Way and Andromeda 2.5 million light-years in just a few billion years. By the time it arrives, its birthplace may have long since merged with another galaxy, erased by the relentless churn of cosmic time. What makes these extreme exiles so fascinating isn't just their distance, it's what their isolation reveals. Without the light pollution of nearby stars, astronomers can study them with unprecedented clarity, as if peering through a perfectly clean window into the universe's depths. Their light, untarnished by interstellar dust or gas, carries pristine information about the composition of their birth galaxies, preserved like a message in a bottle from eons past. Some may even be relics from the universe's infancy, stars flung free before their galaxies fully formed, making them time capsules from an era when the cosmos was young. Yet their loneliness is also a kind of freedom. In the void, these stars are untouched by the gravitational turbulence of galactic cores or the violent births and deaths of stellar neighbors. They burn steadily, undisturbed, their planetary systems, if they have any, free from the asteroid bombardments or gravitational disruptions that plague stars in denser regions. A planet orbiting one of these castaways might enjoy stability lasting hundreds of billions of years, its night sky frozen in perfect, unchanging darkness. But there's a haunting inevitability to their journeys. As the universe expands, the space between galaxies grows ever wider, stretching the void these stars traverse into an even vaster abyss. A star ejected today might one day find itself so far from any galaxy that even the collective glow of all the universe's structures fades into invisibility. Its light, still shining bravely, would travel forever without ever reaching another celestial shore, a beacon with no one left to see it. These loneliest stars are more than just curiosities. They're reminders of the universe's scale, its indifference, and its boundless capacity for isolation. Yet in their solitude, they also offer something rare, a glimpse of the cosmos stripped bare, where the only story is the star itself, burning silently against the endless night. Spotting a lone star in the vast emptiness between galaxies is like trying to find a single flickering candle in a desert the size of a continent. The challenge isn't just their distance, it's the sheer darkness that surrounds them. Without the backdrop of a galaxy's glow, these cosmic orphans often vanish into the black, their light so faint even our most powerful telescopes strain to catch a glimpse. Yet astronomers have developed ingenious ways to track them down, turning their isolation into a clue. One of the most dramatic telltale signs is speed. Hypervelocity stars streaking through space at millions of miles per hour are almost always exiles with a story to tell. Their incredible velocity betrays a violent past, a close encounter with a supermassive black hole or the gravitational slingshot of a galactic collision. These stars don't just drift, They race, their motion so extreme it defies the typical orbits of stars still bound to their galaxies. Catching them requires precise measurements of their movement, like tracing the arc of a bullet fired into the night. But not all orphans are so obvious. Some move more slowly, their faint glow barely distinguishable from the background noise of the universe. To find these elusive wanderers, astronomers rely on deep field surveys, long-exposure images that peer into the darkest corners of space, collecting every possible photon over hours or even days. These observations reveal objects so dim they'd otherwise be invisible, like spotting a firefly against a pitch-black sky. The Hubble Space Telescope's ultra-deep field, for instance, uncovered galaxies billions of light-years away, but nestled among them were a handful of stars that didn't belong, their light signatures hinting at a solitary existence far from any galactic home. Another clue lies in composition. Stars born in different galaxies often carry distinct chemical fingerprints, trace elements forged in their birth clouds or inherited from ancient supernova. By analyzing the light spectrum of a star, astronomers can determine whether it matches its surroundings or stands out as an outsider. A star rich in heavy metals might be a refugee from a galaxy's crowded core, while one with unusually pristine hydrogen could be a relic from the early universe, drifting unchanged for billions of years. Perhaps the most surprising tool in this cosmic hunt is gravity itself. Even invisible, dark matter leaves its mark on the paths of orphaned stars, subtly bending their trajectories like unseen hands nudging them along. By mapping these deviations, scientists can infer the presence of dark matter halos, the invisible scaffolding that shapes the universe's largest structures. Every orphaned star becomes a tracer, its motion sketching the outlines of forces we can't see. What makes these discoveries so thrilling isn't just the stars themselves, but what they reveal about the cosmos. Each one is a data point in a grander puzzle, helping astronomers reconstruct the history of galactic collisions, the distribution of dark matter, even the future of our own Milky Way. And as telescopes grow more powerful, like the upcoming Nancy Grace Roman Space Telescope, designed to scan vast swaths of sky with unprecedented clarity, the number of known orphans will multiply, painting a richer picture of the universe's hidden dynamics. The void, it turns out, isn't empty at all. It's a highway of exiled stars, each carrying secrets from the places they once called home. Among the countless stars adrift between galaxies, a rare few defy all expectations, not just wandering, but hurtling through space at speeds so extreme they could cross the distance from Earth to the Moon in mere minutes. These are hypervelocity stars, cosmic projectiles flung across the universe by forces almost beyond comprehension. Imagine a pinball launched not just off the table, but out of the arcade entirely, racing down the street at impossible velocity. That's the essence of these stellar speed demons, born from some of the most violent encounters the universe has to offer. The secret behind their blistering pace lies in the gravitational jaws of supermassive black holes. Lurking at the centers of galaxies, these cosmic monsters possess gravity so intense they can tear stars apart, or, in rare cases, slingshot them into the void. Here's how it happens. When a binary star system, two stars orbiting one another, ventures too close to a black hole, the immense tidal forces can rip the pair apart. One star gets captured, spiraling into oblivion, while the other is ejected at astonishing speeds, a celestial rubber band snapped with unimaginable force. The energy transfer is so efficient that these ejected stars can reach velocities exceeding 1,000 kilometers per second, fast enough to escape not just their home galaxy, but the gravitational pull of the entire galactic cluster. What makes hypervelocity stars so captivating isn't just their speed, but the stories etched into their paths. Unlike slower orphans, which might meander aimlessly, these stars travel in near-perfect straight lines, their trajectories pointing back like cosmic arrows to the black holes that expelled them. Astronomers have traced some hypervelocity stars all the way to the heart of the Milky Way, confirming their origin in the supermassive black hole at our galaxy's core. Others, however, seem to come from nowhere, their path suggesting they were hurled into intergalactic space by black holes in distant galaxies, making them true interstellar interlopers. Their extreme speed also reshapes their very structure. Racing through the thin gas of intergalactic space, hypervelocity stars plow through the medium like ships through water, their fronts compressed into shock waves while their tails stretch into wispy trails of heated gas. Some even develop bow shocks, glowing arcs of material pushed ahead of them, visible in ultraviolet light like cosmic headlights piercing the darkness. And because they move so quickly, they age differently than their stationary counterparts. Time dilation, an effect of Einstein's relativity, means a hypervelocity star's clock ticks ever so slightly slower compared to stars at rest, a subtle but measurable quirk of physics that adds another layer of intrigue to these already extraordinary objects. Yet for all their drama, hypervelocity stars are more than just cosmic curiosities. They're vital tools for understanding the universe. By studying their speeds and trajectories, astronomers can map the distribution of dark matter, whose gravitational influence subtly bends the paths of even the fastest stars. Their chemical compositions reveal the conditions of their birth galaxies, preserved like fingerprints in their light. And perhaps most remarkably, they serve as test subjects for gravity itself, allowing scientists to probe the limits of Einstein's theories in environments far more extreme than any laboratory on Earth. The existence of hypervelocity stars forces us to rethink what's possible in the cosmos. They prove that black holes aren't just destroyers, they're also cosmic catapults, capable of launching stars across unimaginable distances. They remind us that even in the vast, seemingly empty stretches between galaxies, the universe is alive with motion, with stories of escape and survival written in starlight. And for every hypervelocity star we've discovered, there are surely thousands more racing unseen through the void, each carrying secrets about the violent, beautiful chaos that shapes our universe. Dark matter's invisible hand shapes the cosmos in ways we're only beginning to understand, and its influence might be the hidden architect behind some of the universe's loneliest stars. Though we can't see dark matter directly, its gravitational pull weaves through galaxies like an unseen scaffold, holding them together while simultaneously setting the stage for stellar exile. Picture a vast, intricate spiderweb, its strands invisible except for the way they tug at everything that passes by. That's dark matter's role in the universe, silent, pervasive, and powerful enough to alter the fates of stars. One of the most striking ways dark matter contributes to orphaned stars is through its role in galactic collisions. When galaxies merge, their visible stars and gas clouds aren't the only things interacting. Their dark matter halos collide too, creating gravitational chaos. These halos, stretching far beyond a galaxy's luminous edges, can warp the paths of stars caught in their wake, flinging some outward like stones from a slingshot. It's a bit like stirring a pot of water with unseen currents. The stars respond to forces they never directly touch. Some simulations even suggest that dark matter's gravitational tides might eject stars at higher velocities than galaxy mergers alone, hurling them deeper into the void. But dark matter's influence isn't just about brute force. Its distribution also determines how galaxies evolve and how easily stars slip free. In galaxies with lopsided or clumpy dark matter halos, gravitational imbalances can gradually nudge stars toward escape velocity, a slow-motion ejection that unfolds over billions of years. Other stars might find themselves in regions where dark matter's pull counteracts the galaxy's visible mass, creating temporary gravitational sweet spots that propel them outward. Over time, these subtle nudges add up, turning what might have been a stable orbit into a one-way ticket into the abyss. The most tantalizing clue linking dark matter to orphan stars comes from their trajectories. Many intergalactic wanderers move in ways that can't be explained by visible matter alone. Their paths curve strangely, as if tugged by invisible anchors. Some even appear to cluster in streams, following faint, winding routes through the void that trace the outlines of long-vanished dark matter structures. These phantom highways, woven from dark matter's gravity, could be guiding stars across cosmic distances we're only starting to map. What's remarkable is how these invisible forces leave visible fingerprints. By studying the motions of orphan stars, astronomers can reverse engineer the dark matter landscapes they've traversed, turning stellar outcasts into cosmic surveyors. Each lonely star becomes a probe, its journey revealing the shape and strength of dark matter's grip on the universe. And as we uncover more of these connections, a deeper truth emerges. The story of Galactic Orphans isn't just about stars losing their homes. It's about the hidden architecture of reality itself, a universe where even the emptiest spaces are alive with unseen forces, sculpting destinies in the dark. Galaxies aren't the peaceful islands of light they appear to be. They're voracious predators, consuming their neighbors in a slow-motion feast that reshapes the cosmos. When a massive galaxy collides with a smaller one, it doesn't just absorb it neatly. The gravitational tides pull and twist the smaller galaxy apart, scattering its stars like crumbs from a cosmic table. This is galactic cannibalism, one of the universe's most dramatic forces and one of the primary factories for orphan stars. Take the Milky Way's own history. Right now, our galaxy is in the process of digesting several smaller satellite galaxies, their stars slowly being absorbed into our spiral arms, but not all of them make it. Some are flung outward by gravitational slingshots, ejected into the darkness beyond our galaxy's edge. These stars don't just fade away, they become intergalactic nomads, their trajectories marking the violence of their expulsion. The Sagittarius dwarf spheroidal galaxy, for instance, has been stretched into a stellar stream around the Milky Way, its stars siphoned away over billions of years. Some of those stars didn't settle into new orbits, they were hurled into the void, destined to drift forever. The mechanics behind this stellar exile are both beautiful and brutal. When galaxies merge, their gravity doesn't act like a smooth, uniform force, it's chaotic, with regions of intense tidal shear where stars can be ripped from their orbits. Picture two whirlpools colliding in water. The edges churn unpredictably, flinging droplets in all directions. In galactic mergers, those droplets are stars, some accelerated so violently they reach escape velocity in seconds. The larger the size difference between the merging galaxies, the more extreme the disruption. A dwarf galaxy falling into a giant like Andromeda doesn't just fade into the background, it's shredded, its stars scattered like confetti in a hurricane. But the aftermath holds clues to deeper mysteries. The distribution of orphan stars around a galaxy acts like a fossil record, preserving the history of its mergers. Streams of stars arcing through the halo of the Milky Way, for example, trace the paths of long-devoured galaxies, their structures still visible billions of years later. These stellar ghosts tell us not just about past collisions, but about dark matter's role in shaping them. The way stars are flung outward, their speeds, their angles, reveals the invisible gravitational scaffolding of the galaxies involved. What's startling is the scale of this phenomenon. Current estimates suggest that up to half the stars in the universe's outskirts might be orphans, exiled by galactic cannibalism. Some could even carry planets with them, frozen worlds orbiting stars untethered from any galaxy. Imagine a civilization rising on such a planet. Their night sky wouldn't feature a Milky Way-like band of light, just a scattering of faint, distant galaxies, their sun the only constant in an otherwise empty universe. Yet these violent mergers aren't just destructive, they're creative forces. The same chaos that ejects stars also stirs gas clouds, triggering new waves of star formation in the surviving galaxy. The orphans might be lost, but their sacrifice fuels rebirth elsewhere. It's a reminder that the universe thrives on cycles of destruction, of exile, and ultimately of renewal. Every orphaned star is a testament to the dynamism of the cosmos, a silent witness to the fact that even the grandest structures in space are never truly at rest. Stars that evolve in isolation face a cosmic existence unlike anything within the bustling heart of a galaxy. Freed from the gravitational tug of war of dense stellar neighborhoods, their life cycles unfold in eerie quiet, no nearby supernova to shock their atmospheres, no passing stars to disrupt their orbits, just the slow, unbroken burn of nuclear fusion in perfect solitude. For smaller stars like red dwarfs, this isolation is a gift of longevity. In a galaxy, even these frugal burners might occasionally encounter dense gas clouds or gravitational disturbances that alter their evolution. But in the void, they sip their hydrogen reserves undisturbed, their lifespan stretching toward trillions of years, outliving not just their galactic siblings, but potentially the era of star formation itself. Massive stars, by contrast, face a stranger fate. Normally, their brief, fiery lives end in spectacular supernovae that enrich their surroundings with heavy elements. But an orphan giant has no audience for its demise. When it exhausts its fuel, its death explosion lights up the emptiness with no nearby gas to absorb its ejected material. The resulting nebula, rich in carbon, oxygen, and iron, drifts eternally, a ghostly cloud with no planets or new stars to inherit its elements. Even the stellar remnant left behind is different. Without the dense environment of a galaxy, a collapsing massive star might form a black hole with an unusually quiet accretion disk, or a neutron star that spins down without ever becoming a pulsar. These isolated remnants cool into darkness, their incredible densities hidden in the void. Then there are the middleweight stars like our Sun. In a galaxy, their eventual transformation into white dwarfs is often just the beginning of a new chapter. Planetary nebulae shed from their outer layers mingle with interstellar gas, while their exposed cores slowly crystallize over eons. But an orphaned sun-like star has no such interactions. Its planetary nebula expands unseen, dissipating into the near-perfect vacuum of intergalactic space. The white dwarf it leaves behind cools in total isolation, its heat radiating away into nothingness until it becomes a black dwarf, a cold, dark diamond the size of a planet, floating forever in the dark. The most fascinating outliers might be the stars that shouldn't exist at all. In galaxies, ultra-massive stars often shed their outer layers through fierce stellar winds or binary interactions, preventing them from growing too large. But in isolation, a star could theoretically accrete gas from a rare intergalactic cloud without disruption, ballooning into a behemoth with hundreds of solar masses. Such a star would burn impossibly bright and die young, its collapse potentially forming an intermediate mass black hole, a rarity in the modern universe. Even more bizarre are the hypothetical frozen stars, objects so isolated that their outer layers cool before death, forming exotic, super-dense states of matter unseen in galactic environments. Yet the true legacy of these stellar hermits lies in what they teach us about resilience. A star's evolution isn't just dictated by its mass and composition, but by its surroundings or lack thereof. The same processes that create pulsars, nebulae, and black holes in galaxies unfold differently in the void, offering astronomers a controlled experiment on cosmic scales. Every orphaned star is a laboratory, its isolation stripping away the noise of galactic life to reveal the fundamental physics governing all stars. And in their quiet, unwavering glow, they prove that even in the universe's emptiest corners, the laws of nature persist unobserved but unbroken. Among the countless orphans of the cosmos, some wanderers defy expectations, not blazing stars, but dark, frozen worlds adrift in the endless night. These rogue planets, untethered from any solar system, might be the universe's silent majority. Current estimates suggest there could be trillions of them drifting unseen between galaxies, outnumbering stars by as much as 20 to 1. Picture a planet like Jupiter, but ripped from its orbit and hurled into the void, its atmosphere slowly freezing into an icy crust as it tumbles through temperatures near absolute zero. Without a sun to warm it, such a world becomes a ghost, a frigid nomad carrying the remnants of its lost solar system into oblivion. How does a planet end up so utterly alone? The process begins with chaos. When a star is ejected from its galaxy, whether by a black hole's slingshot or a galactic collision, any planets orbiting it face a grim choice: follow their host into exile or break free entirely. Most are torn away by gravitational turbulence during the ejection, sent spiraling into darkness without even the faint glow of their star to guide them. Others might be stripped from their orbits later, as passing stars or interstellar clouds tug them loose. The cruelest fate belongs to planets in binary star systems. When one star is captured by a black hole, its companion, and any orbiting worlds can be flung outward at terrifying speeds, destined to cross intergalactic space alone. The surfaces of these orphaned worlds are landscapes of unimaginable cold. With no external heat source, their atmospheres collapse into snow, their oceans freeze solid to the core. Any gases that once warmed them, methane, nitrogen, even oxygen, become icy veneers coating barren rock. Yet beneath this frozen shell, surprises might linger. Tidal forces from a massive planet's own moon, or residual geothermal heat from radioactive decay, could maintain subsurface oceans of liquid water. In the icy depths of Europa or Enceladus, we've seen how such hidden seas might harbor life. An orphan planet, drifting for billions of years, could carry its own secret oasis, a pocket of warmth in the eternal dark. What's astonishing is how many of these worlds might exist. Modern telescopes have detected rogue planets even within our galaxy, some so young they still glow faintly from the heat of formation. But the true population lies in the intergalactic void, where the darkness hides them from view. Their presence is inferred through microlensing, a phenomenon where a planet's gravity briefly bends the light of a distant star like a cosmic magnifying glass. These fleeting distortions hint at an unseen multitude, a hidden architecture of worlds adrift between the galaxies. Yet for all their isolation, orphan planets aren't just cosmic curiosities, they're time capsules. A rogue planet's composition preserves the chemistry of its birth nebula, uncontaminated by billions of years of stellar winds or supernova debris. Some might even carry the building blocks of life, frozen in stasis since their ejection. And if, by some infinitesimal chance, life did arise on such a world before it was cast adrift, it might persist in those dark, pressurized oceans, utterly unaware that stars or galaxies even exist. The existence of these wanderers forces us to reconsider what makes a planet. Must it orbit a star, or is the universe teeming with worlds that defy that definition: dark, solitary spheres tracing endless paths through the void? They remind us that the cosmos is stranger than we imagine, filled with orphans of every kind, each carrying fragments of stories we've only begun to decipher. Most stars don't travel alone when they're cast into the void. They drag entire worlds with them. The idea of an orphaned solar system might sound like science fiction, but the cosmos has a way of turning the improbable into reality. Imagine a star not just solitary but surrounded by a retinue of planets, all flung together into the intergalactic dark. These nomadic systems are among the rarest objects in the universe, requiring a perfect storm of conditions to survive ejection intact. Yet against all odds, some do. The key lies in the violence of their departure. When a star is hurled from its galaxy, whether by a close encounter with a supermassive black hole or the gravitational chaos of a galactic collision, its planets face a brutal test. If the ejection is too abrupt, the star's gravitational grip can falter, sending its worlds spiraling away like marbles dropped on a trampoline. But if the star is nudged gently toward escape velocity, its planetary family might hold on, their orbits stretched but unbroken. It's a cosmic balancing act, enough force to escape the galaxy's pull, but not so much that the star's own planetary system shatters. One of the most likely scenarios for this delicate escape involves binary stars. When two stars orbit each other tightly, their combined gravity can act like a shield, stabilizing their planets against external turbulence. If one star is captured by a black hole, the other might be ejected with such precision that its planets barely notice the disturbance. Astronomers have even theorized about hypervelocity solar systems, entire planetary families racing through space at thousands of kilometers per second. Their star's velocity so extreme it defies belief, yet their worlds remain dutifully in tow. But survival doesn't end with ejection. The real challenge begins in the void. Without the gentle pressure of interstellar gas or the occasional gravitational nudge from passing stars, an orphaned solar system's orbits can grow unstable over time. Planets might gradually drift outward, their stars' light too faint to warm them, or spiral inward, drawn by tidal forces. Moons could escape their parent planets entirely, becoming miniature worlds adrift in a system already adrift. Yet for those that endure, the conditions are strangely pristine. No asteroid bombardments from neighboring stars, no violent supernova to blast away atmospheres, just the slow, quiet evolution of a system untouched by the chaos of galactic life. What would it be like to stand on a planet in such a system? The night sky would be a study in loneliness. No neighboring stars, no Milky Way stretching overhead, just the faint glow of distant galaxies, their light diluted by millions of light years. The sun would hang in perpetual midday, never rising or setting, its light feeble compared to the brilliance of a star anchored in a galaxy. Seasons would vanish. Without the gravitational perturbations of other stars, the planet's axial tilt might remain fixed for eons. Life, if it existed, would evolve under a sun that never moves, on a world where the concept of night is meaningless. The existence of these rogue systems forces us to rethink the boundaries of habitability. A planet orbiting an orphaned red dwarf, for instance, might huddle close enough to bask in its star's meager warmth, its oceans kept liquid by geothermal vents or thick insulating atmospheres. Microbial life could persist in these isolated pockets, cut off from the rest of the universe but enduring nonetheless. And if intelligent life arose, its view of the cosmos would be profoundly different. No stars to navigate by, no galactic neighbors to signal, just the endless dark and the faint smudges of faraway islands of light. Yet for all their isolation, orphaned solar systems aren't entirely cut off from the universe. They still feel the tug of dark matter, the expansion of space, the rare passage of other exiled stars. Some might even drift close enough to one another to form temporary clusters, their stars passing like ships in the night before continuing their solitary journeys. And in the far future, when galaxies have merged and faded, these nomadic systems could be the last bastions of warmth in a cooling cosmos, their stars burning long after the galactic lights have gone out. The rarest of the rare, these wandering systems remind us that the universe is full of exceptions to every rule. For every star torn from its planets, there might be one that held on. For every world cast into the dark alone, there could be a family of worlds traveling together, their bonds unbroken by the void. They are proof that even in the coldest, emptiest reaches of space, the universe still finds ways to surprise us. At the heart of nearly every galaxy lurks a gravitational monster, a supermassive black hole with the power to reshape stellar destinies. These cosmic behemoths, weighing millions or even billions of times the mass of our sun, don't just swallow stars, they catapult them across the universe. The process begins with a simple cosmic rule. What goes near a black hole doesn't always go in. Sometimes it comes out faster, much faster. Picture a star system drifting too close to the black hole's crushing grip. As the black hole's gravity stretches and warps space around it, the star system doesn't just fall straight in. It gets whipped around like a tetherball, its trajectory bent to impossible angles. In many cases, one star gets captured, spiraling toward oblivion, while its companion is flung outward at velocities that defy imagination. This is the gravitational slingshot effect in its most extreme form, a natural particle accelerator hurling stars at speeds exceeding 1,000 kilometers per second. The ejected star doesn't just escape its galaxy. It becomes a hypervelocity fugitive, racing toward intergalactic space with enough momentum to cross the void between galaxies in mere cosmic moments. But slingshots aren't the only way black holes exile stars. Chaotic multi-body interactions near galactic centers can turn stellar orbits into cosmic pinball games. When several stars and black holes interact simultaneously, their combined gravitational forces create unpredictable chaos. A star might get a series of glancing blows from other objects, each kick adding to its speed until it's ejected entirely. These events are like celestial billiards played on an unimaginable scale where instead of balls, the players are stars, and the table is the warped space around a black hole. The aftermath of these violent encounters leaves behind unmistakable fingerprints. Hypervelocity stars move in near-perfect straight lines, their paths pointing directly back to the galactic center like cosmic breadcrumbs leading to the black hole that expelled them. Their compositions often reveal clues. Two stars rich in heavy elements might hint at a violent past near the turbulent core, while others show signs of being ripped from binary systems. And then there's the speed itself. Unlike stars ejected by galaxy collisions, which typically move a few hundred kilometers per second, black hole-launched stars can reach velocities so high they're effectively unbound from the universe's largest structures. What makes these events so fascinating isn't just the physics, it's the scale of destruction and creation at play. For every star flung into the void, another might be torn apart, its material feeding the black hole in a brilliant tidal disruption flare. Others could be sent careening into new orbits, destined to become eccentric outliers in their own galaxies. And in rare cases, planets orbiting these stars might survive the ordeal, dragged along on an interstellar journey with no return ticket. These stellar fugitives are more than just cosmic oddities, they're messengers. By tracing their paths, astronomers can map the invisible influence of supermassive black holes, measure the distribution of dark matter, and even test the limits of Einstein's theory of gravity. Each hypervelocity star is a testament to the raw power lurking at the heart of galaxies, proof that even the darkest objects in the universe can set the stage for the most extraordinary escapes. Every orphaned star carries a hidden record of its past, not in words, but in the very elements that make up its fiery heart. Like cosmic archaeologists sifting through stellar dust, astronomers use a powerful tool called spectroscopy to decode these ancient stories. When starlight passes through a prism or diffraction grating, it splits into a rainbow of colors. But this rainbow isn't perfect. Dark lines streak across it, each one a fingerprint left by specific elements in the star's atmosphere. Iron, carbon, oxygen, every atom absorbs light at unique wavelengths, creating a barcode that reveals the star's chemical identity. For orphaned stars, this barcode is a treasure map pointing back to their origins. Take a star rich in heavy metals like gold or uranium. These elements aren't forged in ordinary stellar cores, they're born in the violent explosions of supernova or the collisions of neutron stars. A star bearing their signature likely grew up in a bustling galactic neighborhood where such cataclysms were common. Compare that to a star with barely any metals at all. Its pristine composition suggests it formed early in the universe's history, before generations of supernova had seeded space with heavier elements. These metal-poor relics might be refugees from dwarf galaxies, small cosmic backwaters where star formation stalled billions of years ago, but the clues go deeper than just ingredients. The ratios of elements can trace a star's birthplace with startling precision. For example, stars from the Milky Way's disk often have different magnesium to iron ratios than those from its halo, a telltale sign of their galactic address before exile. Some orphaned stars even carry the chemical scars of their ejection event. Stars flung from galactic centers might show unusual abundances of elements like aluminum or sodium, forged in the extreme environments near supermassive black holes. Others bear traces of rapid rotation, a souvenir from the gravitational slingshot that hurled them away. The real magic happens when astronomers match these chemical fingerprints to known galaxies. Imagine finding a star adrift between the Milky Way and Andromeda with a composition nearly identical to stars in the Large Magellanic Cloud. Suddenly, that star becomes evidence of a long-ago encounter between galaxies, a celestial artifact marking a collision that happened billions of years before humans even looked up at the night sky. Other orphans might belong to no known galaxy at all, their unique chemistry hinting at fully dissolved dwarf galaxies or even pristine pockets of the early universe, untouched by galactic mergers. This cosmic detective work isn't just about individual stars, it's reconstructing the family trees of galaxies themselves. When astronomers find groups of orphan stars sharing similar compositions and trajectories, they're likely remnants of the same disrupted galaxy. Like scattered pages from a torn-up book, these stars collectively tell a story of galactic cannibalism, revealing which galaxies our Milky Way has consumed over its lifetime. Some streams of orphans even trace the gravitational pull of dark matter, their paths bending around invisible halos we can't see directly. Spectroscopy transforms these lonely wanderers from celestial curiosities into vital historical documents. Each element, each ratio, each subtle spectral line is a sentence in a story written in starlight, a story of creation, exile, and the invisible forces that shape the universe. And as telescopes grow more powerful, the resolution of these stellar autobiographies will only sharpen, revealing chapters of cosmic history we've only begun to imagine. The destinies of these wandering stars unfold across timescales that dwarf human history, some destined for recapture, others condemned to eternal drift. For a lucky few, the gravitational pull of a passing galaxy might offer salvation. Picture a star ejected from the Milky Way during a long-ago collision. drifting for billions of years until Andromeda's approaching embrace snags it like a cosmic fishing net. The process isn't gentle. As galaxies merge, their overlapping gravitational fields create chaotic zones where orphaned stars can be swept into new orbits, trading one stellar community for another. These recaptured wanderers often end up in the outer halos of galaxies, their trajectories forever marked by their time in the void, like immigrants carrying accents from distant shores. But not every orphan gets a second chance. The majority will continue their solitary journeys, their paths bending slightly under the influence of dark matter, but never close enough to another galaxy to be anchored. Over trillions of years, as the universe expands and galaxies recede from one another, these stars will find the void growing even emptier. Their greatest enemy isn't distance, it's time. Even the longest-lived red dwarfs will eventually exhaust their fuel, cooling into black dwarfs so faint they'd be invisible to any hypothetical observer. The universe's expansion will stretch their light beyond detectability, leaving them as little more than cold, dark monuments to a brighter age. Then there are the rare cosmic collisions, events so improbable they might happen only once in a galaxy's lifetime, but inevitable given enough time. Two orphaned stars, each wandering for billions of years, might cross paths in the void with cataclysmic results. If one is a white dwarf and the other a neutron star, their merger could trigger a kilonova, an explosion so violent it briefly outshines every star in the local universe. More haunting are the near misses, stars passing close enough to perturb each other's trajectories but not collide, their gravitational dance altering their fates forever. These interactions are the universe's way of reminding us that even in the emptiest reaches, nothing is truly alone. The most poetic fate belongs to orphans carrying planets. A rogue world orbiting an exiled star might drift close enough to another stellar outcast to be captured, trading one parent star for another in a celestial adoption spanning eons. Alternatively, a close encounter could slingshot the planet free entirely, leaving it to wander the darkness alone, a second-generation orphan with no memory of its original home. In the coldest corners of the cosmos, these chance meetings rewrite stellar genealogies, creating lineages as tangled as they are ancient. What binds all these fates together is the inevitability of change. Whether recaptured, collided, or condemned to endless drift, galactic orphans are testament to the universe's restlessness. They prove that even the most stable-seeming systems are temporary, and that gravity's reach, while vast, has limits. Long after the galaxies they once knew have merged, faded, or transformed beyond recognition, these wanderers will still be traveling, their stories etched in trajectories only the cosmos itself can read. The universe isn't just expanding, it's accelerating, stretching the fabric of space itself at a rate that grows faster with every passing moment. For orphaned stars adrift between galaxies, this cosmic expansion isn't just background noise, it's a one-way ticket into oblivion. Imagine being on a raft in the middle of the ocean, only to watch the shorelines on either side recede faster than you could ever paddle toward them. That's the fate of these stellar castaways as the space around them stretches, carrying galaxies and any hope of reunion farther and farther away. At first, the effect is subtle. A star ejected from the Milky Way today might drift for billions of years before feeling the full force of cosmic expansion. But over time, the relentless pull of dark energy, the mysterious force driving the universe's acceleration, becomes undeniable. Distances that once seemed vast grow insurmountable. A star that started its journey a million light-years from the nearest galaxy could find itself twice as far given enough time, not because it's moving, but because the space between it and everything else is growing like an inflating balloon. The farther apart two objects are, the faster space expands between them, meaning the most isolated orphans face the cruelest exile. Some of these stars will reach a point of no return. Beyond a certain distance, the expansion of space outpaces even the speed of light, at least locally. This doesn't mean the star is moving faster than light, nothing can, but the space between it and us grows so quickly that its light will never reach us again. These stars don't just fade, they vanish from the observable universe entirely, their light stretched into wavelengths so long they become undetectable. It's as if they've crossed a cosmic event horizon, slipping beyond the reach of any future telescope, no matter how advanced. Yet in their isolation, these stars become accidental probes of the universe's most profound mysteries. Their trajectories measured against the backdrop of galaxies help astronomers map the expansion rate of the cosmos with unprecedented precision. Some might even pass through regions of space where dark energy's influence wavers, offering clues to whether this force is truly constant or changes over time. And because their light takes eons to reach us, studying the most distant orphans is like looking back in time, capturing snapshots of the universe's expansion history written in starlight. The irony is haunting. Stars born in the crowded heart of galaxies, surrounded by siblings and planets, end their lives as cosmic lighthouses in a darkness so complete no one will ever see their glow. Their stories, written in redshift and trajectory, tell of a universe growing colder, emptier, and more fragmented with each passing eon. And as the acceleration continues, even the closest galaxies will one day slip beyond the horizon, leaving any remaining orphans in a void without landmarks, without witnesses, without end. To unravel the violent origins of orphaned stars, astrophysicists turn to supercomputers, digital laboratories where galaxies collide and black holes fling stars into the void with the click of a mouse. These simulations aren't just animations, they're mathematical time machines crunching billions of calculations to recreate the exact conditions that tear stars from their homes. Picture a virtual Milky Way, its stars rendered as points of light, each governed by equations dictating how gravity, motion, and cosmic turbulence interact. When scientists introduce a simulated collision with another galaxy, the digital stars don't just bump politely, they ricochet, spiral, and sometimes erupt outward like sparks from a fire, mirroring the chaos of real cosmic encounters. One of the most revealing models focuses on the slingshot effect near supermassive black holes. By programming in Einstein's equations of relativity alongside stellar physics, researchers can watch as a binary star system approaches the black hole's event horizon. The simulation captures the precise moment when one star is captured, its partner flung away at velocities exceeding 2,000 kilometers per second, a speed that would take it from Earth to the Moon in under 3 minutes. These digital experiments show that the angle of approach is everything. A slight difference of a few degrees can mean the difference between a star being swallowed or becoming a hypervelocity exile. But black holes aren't the only ejection engines. Galactic mergers like the impending collision between the Milky Way and Andromeda require even more complex simulations. Here, dark matter's invisible influence becomes a critical variable. Models must account for the way dark matter halos warp spacetime during a merger, creating gravitational tides that can hurl stars far beyond the visible edges of either galaxy. Recent simulations revealed something startling. Up to 20% of stars in merging galaxies might be ejected into intergalactic space, their fates determined by chaotic three-body interactions between stars, gas clouds, and dark matter's unseen pull. The real power of these models lies in their predictive ability. When astronomers compare simulation results to actual observations of hypervelocity stars or orphaned star streams, the matches are often uncanny. For example, a simulation of the Sagittarius Dwarf galaxy's disruption by the Milky Way predicted trails of ejected stars that were later found in telescope surveys. Other models have pinpointed where to search for orphaned stars based on their expected chemical compositions, like cosmic treasure maps leading to relics of ancient galactic violence. Yet simulations also expose gaps in our understanding. Some ejected stars move faster than models predict, hinting at unknown physics near black holes or the possibility of primordial black holes amplifying gravitational kicks. Others show orbital paths that don't align with any known galactic collision, suggesting entire chapters of cosmic history we've yet to uncover. Each discrepancy is a puzzle and an invitation to refine the virtual universe further. What's extraordinary is how these digital experiments transform abstract math into tangible stories. A simulation isn't just lines of code, it's a bridge between theory and observation, letting us witness events too slow or distant to study directly. Through them, we've learned that orphaned stars aren't accidents. They're inevitable byproducts of a dynamic, ever-changing cosmos. And as supercomputers grow more powerful, these virtual laboratories will continue to reveal the hidden mechanics behind the universe's loneliest wanderers, one calculation at a time. Our Milky Way's orphans are far from unique. Galaxies across the universe are constantly shedding stars, each ejection telling its own story of cosmic violence. Take Andromeda, our closest galactic neighbor. Astronomers have spotted vast streams of stars arcing around it like celestial ribbons, remnants of smaller galaxies it has devoured over billions of years. But not all those stars stayed bound. Some were flung into the void during the chaos of collision, their trajectories mapping the gravitational fury of Andromeda's appetite. These exiles drift in its halo, a ghostly testament to mergers long past. Then there's the Sombrero Galaxy, a stunning spiral with a halo so thick with orphaned stars it resembles a cosmic aurora. Unlike the Milky Way's scattered outcasts, many of these stars seem to have been ejected not by collisions, but by the galaxy's own turbulent core. Its supermassive black hole, far more active than ours, acts like a gravitational cannon, firing stars into the darkness at speeds that defy imagination. Spectroscopy reveals their compositions are laced with rare elements, chemical fingerprints of the extreme environments near the black hole's maw. But not all ejections are so dramatic. In the Leo I Dwarf galaxy, a tiny satellite of the Milky Way, stars slip away quietly like sand through fingers, with gravity too weak to hold them tightly. Even passing gas clouds or minor interactions can nudge stars free. These aren't hypervelocity exiles, they're drifters, moving just fast enough to escape but so slowly their departure takes eons. Their faint glow, barely distinguishable from the background, makes them some of the hardest orphans to spot. Yet their very existence reveals a universal truth. No galaxy, big or small, holds onto all its stars forever. The most extreme examples lie in galaxy clusters, where hundreds of galaxies orbit one another in a gravitational dance. Here, the sheer density of interactions creates a stellar free-for-all. Stars are ripped from their homes not just by individual galaxies, but by the collective gravity of the entire cluster. The result, a diffuse cloud of orphans buzzing between galaxies like bees in a meadow. Some may never belong to another galaxy again. Instead, they'll spend eternity as true intergalactic nomads, their loyalties erased by the chaos of the cosmos. What's striking is how these observations mirror and sometimes challenge what we see in our own backyard. The Milky Way's hypervelocity stars have counterparts in Andromeda, but their ejection mechanisms vary. Our galaxy's orphans often trace back to dwarf galaxy collisions, while in massive ellipticals like M87, black hole slingshots dominate. these differences aren't just academic, they're clues to how galaxies evolve. A preponderance of collision-driven orphans hints at a violent merger history, while black hole ejected stars betray the ferocity of a galaxy's core. Yet amid the diversity, one pattern holds true: orphaned stars are universal. Every galaxy, no matter its size or shape, contributes to this cosmic diaspora. And as telescopes peer deeper into the void, they're finding these exiles everywhere, threading through the spaces between galaxy clusters, lingering in the wakes of galactic collisions, even congregating in unexpected pockets where gravity has herded them like celestial sheep. Their ubiquity is a reminder that the universe is in constant flux, its structures both grand and ephemeral. For every star born in a galaxy's embrace, another is destined to wander, an eternal traveler in the dark. Science fiction has always had a knack for predicting, or at least paralleling, the strangest truths of the cosmos, and Galactic Orphans are no exception. Long before astronomers confirmed the existence of stars adrift between galaxies, storytellers were imagining the haunting possibilities of these cosmic loners. Take the 1966 Star Trek episode, The Immunity Syndrome, where the Enterprise encounters a rogue planet hurtling through space, devoid of any solar system. The crew describes it as a cosmic ghost town, a phrase that eerily mirrors how scientists now speak of real orphaned worlds frozen, isolated, and untethered. What's striking is how fiction often amplifies the loneliness of these objects, turning them into metaphors for exile or resilience. In The Hitchhiker's Guide to the Galaxy, the planet Magrathea isn't just rogue, it's a hidden factory for custom worlds, playing on the idea that the void might harbor secrets too strange for textbooks. But sci-fi doesn't just romanticize orphaned stars, it grapples with their physics. In Rendezvous with Rama, Arthur C. Clarke envisioned an interstellar asteroid, a nomadic rock tumbling between stars, as the setting for first contact. Decades later, astronomers discovered Oumuamua, our first confirmed interstellar visitor, proving reality can be as puzzling as fiction. Meanwhile, films like Interstellar take the opposite approach, portraying rogue planets not as lifeless husks but as potential havens. The ice-covered world orbiting Gargantua's black hole teeters between scientific plausibility and creative liberty, imagining a planet warmed by tidal forces rather than a sun, a nod to real theories about orphaned worlds with subsurface oceans. The trope of the wandering Earth in Chinese sci-fi, popularized by Liu Cixin's The Wandering Earth, takes the concept to apocalyptic extremes. Here, humanity straps engines to our planet to flee the dying sun, turning Earth itself into a galactic orphan. It's a fantastical premise, but one that echoes the real-world fate of stars ejected from galaxies, just on a more relatable scale. Even horror taps into the dread of isolation. Event Horizon's titular ship isn't just lost in space, it's adrift in a realm where the laws of physics break down, mirroring the disorientation a real star might face in the intergalactic void, untethered from the familiar pull of a galactic home. What unites these stories is their obsession with the same questions astronomers ask. What happens to something or someone cut off from its origins? Can survival in the void reshape identity? Fiction's answer often leans toward drama, but the underlying themes resonate with scientific reality. Orphaned stars do evolve differently in isolation. Rogue planets might harbor life against all odds. The line between sci-fi speculation and astrophysical discovery blurs when you consider that some of the universe's strangest truths were dreamed up by storytellers first. Whether as metaphors or plot devices, Galactic Orphans remind us that the cosmos's loneliest phenomena are also its most fertile ground for imagination. Could life cling to existence on a planet with no sunrise, Imagine a world orbiting an orphan star where the concept of day doesn't exist, just an eternal twilight lit by a dim, unmoving sun. The surface would be a frozen wasteland, its atmosphere collapsed into ice under temperatures nearing absolute zero. Yet beneath the ice, in the crushing depths of a subsurface ocean kept liquid by geothermal heat or radioactive decay, life might find a way. Earth's own extremophiles organisms thriving in deep sea vents or buried Antarctic lakes prove that where there's energy and water, life can persist against staggering odds. An orphan planet warmed by tidal forces from a massive moon or residual heat from its formation could harbor similar oases in the dark. The chemistry of such a world would be unlike anything in our solar system. Cut off from the ultraviolet radiation and stellar winds that shape planetary atmospheres, its oceans might be rich with molecules preserved from its birth primordial soups untouched by billions of years of galactic weather. Hydrothermal vents, if present, could churn out nutrients in slow, steady cycles, sustaining ecosystems fueled not by photosynthesis, but by chemosynthesis. Life here wouldn't rely on a sun-driven food web. It might resemble the bizarre communities huddled around Earth's deep-sea smokers, where microbes convert minerals into energy and entire ecosystems thrive in total darkness. But the challenges are profound. Without a galaxy's steady supply of comet-delivered water or asteroid-stirred minerals, these worlds could be resource deserts. A rogue planet's biosphere, if it exists at all, might be a single, fragile layer beneath the ice, vulnerable to freezing solid if its heat sources dwindle. Even the star it orbits offers little reprieve. Red dwarfs, the most common orphan stars, are prone to violent flares that could strip atmospheres or irradiate surfaces over time. And if the planet was ejected from its original system after life arose, the shock of sudden isolation, plunging temperatures, vanishing sunlight, would test survival in ways we can barely imagine. Yet the universe loves surprises. Some orphan stars might host planets in tight, tidally locked orbits, where the star's meager warmth keeps one side perpetually thawed. Others could benefit from thick hydrogen atmospheres, trapping geothermal heat like a cosmic pressure cooker. There's even speculation about stealth planets, worlds with subsurface oceans so deep their ice shells insulate them completely, creating pockets of warmth that persist for billions of years. If life exists in these shadowed realms, it would evolve in isolation so extreme its biochemistry might be unrecognizable. The search for such life pushes the boundaries of astrobiology. Future telescopes able to detect atmospheric traces on rogue planets, methane, oxygen, or even technosignatures, could turn speculation into science. For now, these worlds remain hypothetical, their potential stories written in equations and simulations. But they force us to reconsider what habitable really means. Life, it seems, doesn't need a sunny spot in a friendly galaxy. It just needs a chance, and in the endless dark between the stars, chances hide in the unlikeliest places. Not all orphaned stars drift through the void in solitude. Some travel in vast, ghostly processions called stellar streams. These celestial rivers, stretching tens of thousands of light years across the sky, are the remnants of dwarf galaxies or star clusters torn apart by the immense gravitational pull of larger galaxies. Picture a cosmic spiderweb, its delicate strands made not of silk but of stars, each thread tracing the path of a galactic encounter that happened billions of years ago. These streams aren't just random scatterings, they're the shredded skeletons of smaller systems, their stars still moving in unison like a school of fish long after their home has been devoured. One of the most famous examples wraps around our own Milky Way, the Sagittarius Stream. This sprawling arc of stars is all that remains of the Sagittarius dwarf galaxy, a tiny neighbor that ventured too close to our galaxy's gravitational embrace. Over eons, the Milky Way's tide stretched and pulled the dwarf galaxy apart, leaving behind a luminous trail that now encircles us like a cosmic noose. The stars in this stream share a distinct chemical fingerprint, a telltale sign of their common origin, and their paths reveal the exact timeline of their disintegration. By mapping their motions, astronomers can rewind the tape, reconstructing the Milky Way's history of galactic cannibalism. But stellar streams aren't just relics of destruction, they are also cosmic breadcrumbs leading to dark matter. The way these streams bend and warp under invisible forces betrays the presence of dark matter halos, the elusive scaffolding that shapes galaxies. Some streams show kinks or gaps, like a river diverted by hidden boulders. These anomalies suggest encounters with dark matter clumps, offering rare clues about its distribution. In a way, stellar streams are like celestial seismographs, recording the tremors of unseen masses as they ripple through the galaxy. The sheer variety of these streams tells a richer story than any single example. Some, like the Orphan stream, are so named because their origins remain mysterious. No parent galaxy or cluster has yet been found. Others, like the GD1 stream, are nearly pristine, their stars moving in such perfect synchrony that they must have been stripped away gently, like leaves floating from a tree. Then there are the hypervelocity streams, stars racing so fast they're barely bound to the galaxy at all, their trajectories hinting at violent ejections from the supermassive black hole at the Milky Way's heart. What makes these structures so invaluable is their longevity. Unlike the brief flare of a supernova or the chaotic churn of a galactic collision, stellar streams preserve their history for billions of years. They're the universe's way of keeping records, etching its past in starlight. And as telescopes grow more powerful, new streams are being discovered at an astonishing rate, each one a fresh chapter in the story of how galaxies grow, collide, and reshape one another. The next time you look up at the night sky, remember, those faint, distant stars might not be random dots at all. They could be part of an ancient river flowing silently through the cosmos, a river of orphans, bound not by gravity but by shared history. The Milky Way may seem like a stable, swirling metropolis of stars, but hidden among its spiral arms are celestial fugitives, stars moving so fast they're escaping our galaxy entirely. One of the most famous is S5 HVS1, a hypervelocity star racing through space at over 6 million kilometers per hour. Discovered in 2019, this stellar speedster was flung from the Milky Way's core by our supermassive black hole, Sagittarius A, in an event so violent it left the star hurtling toward intergalactic space with enough momentum to never look back. Its trajectory points directly to the galactic center like a cosmic arrow, revealing the black hole's role as both destroyer and catapult. But not all Milky Way orphans come from the same violent origins. The so-called Gaia sausage stars tell a different story, a tale of galactic cannibalism. These stars move in odd, elongated orbits, their paths and chemical compositions betraying them as remnants of a dwarf galaxy that collided with the Milky Way 8 to 10 billion years ago. Unlike hypervelocity stars, which are ejected solo, these orphans arrived as part of a doomed system, their parent galaxy shredded by tidal forces until only scattered stars remained. Today, they form a ghostly imprint of that ancient collision, their motions preserved like fossils in the Milky Way's halo. Then there are the quieter exiles. Stars like He0437 5439 don't move fast enough to escape the galaxy entirely, but their paths are still marked by past trauma. This blue straggler, a star anomalously young and hot for its neighborhood, likely gained its speed during a chaotic gravitational dance in a dense star cluster. Kicked out by a close encounter with other stars, it now drifts through the Milky Way's outskirts, a wanderer with no home cluster to return to. What binds these orphans together is their ability to map the Milky Way's hidden history. By tracing their paths backward, astronomers reconstruct events no telescope could witness directly: the mergers, the near misses, the explosive encounters with black holes. Each one is a clue, and together they reveal a galaxy far more dynamic and violent than its serene spiral appearance suggests. The Milky Way isn't just a home for stars. It's a place where stars are made, broken, and sometimes cast away into the dark. The space between galaxies isn't truly empty. It's a vast, ghostly ocean of superheated gas and dark matter, so thin that a single grain of sand's worth of material might be scattered across a volume the size of a football stadium. This is the intergalactic medium, the near-nothingness that orphaned stars must navigate on their eternal journeys. Unlike the dense, turbulent environments within galaxies, where stars swim through clouds of gas and dust, the intergalactic void offers no resistance, no friction, just an almost perfect vacuum stretching for millions of light years. Yet even here, subtle forces shape the fate of wandering stars in ways both profound and unexpected. One of the quietest but most persistent influences is drag. At first glance, it seems impossible. How could a near-perfect vacuum slow something down? But over cosmic timescales, even the faintest whispers of gas add up. A star plowing through the intergalactic medium at high speed compresses the sparse hydrogen atoms in its path, creating a microscopic bow shock that saps its momentum. The effect is infinitesimal, like a marathon runner feeling the resistance of a single cobweb. But after billions of years, even hypervelocity stars can shed a fraction of their speed, their trajectories bending ever so slightly under this cumulative friction. For slower-moving orphans, the drag might eventually steer them into the gravitational pull of a passing dark matter filament, altering their course entirely. Then there's the rare but spectacular collisions. Every so often, an orphaned star's path intersects with another cosmic castaway, perhaps a rogue planet, a wandering black hole, or even another star. The probabilities are vanishingly small, but given enough time and space, the improbable becomes inevitable. When two stars meet in the void, the outcomes range from graceful dances to cataclysmic mergers. Binary systems can form, their mutual gravity binding them together in an isolated partnership lasting eons. More dramatically, a close pass between a massive star and a compact object like a neutron star might strip away layers of stellar material, leaving behind a glowing trail of ionized gas, a temporary scar in the darkness. The intergalactic medium also plays chemist. In galaxies, stars are constantly bathed in fresh gas and dust, their atmospheres enriched by supernova debris. But orphaned stars must make do with whatever elements they carried at ejection. Over time, the thin intergalactic gas, mostly primordial hydrogen and helium, can accrete onto their surfaces, subtly altering their composition. For smaller, cooler stars, this slow accumulation might extend their lifespans, providing fresh fuel for nuclear fusion. For others, it's a drop in the bucket, barely noticeable against the backdrop of their inevitable cooling. Perhaps the most haunting role of the intergalactic medium is as a storyteller. The way a star moves through it, the slight changes in its velocity, the traces of ionized gas in its wake, records its history like grooves in a cosmic vinyl record. Astronomers can read these clues to determine not just where a star came from, but what it's encountered along the way. A star with a faint shockwave of heated gas ahead of it might have been ejected recently, its journey just beginning. Another with an oddly high metallicity could hint at a long-ago passage through a dense galactic tail, where it scooped up heavier elements like a ship gathering driftwood. In the end, the intergalactic medium is more than just empty space. It's an active participant in the lives of orphaned stars, shaping their journeys in ways both subtle and dramatic. It's the canvas on which their stories unfold, the silent witness to their isolation, and occasionally, the architect of their rare encounters. For stars adrift in this sea of near-nothingness, every atom matters, every interaction leaves a mark, and even the void itself has a voice. Not all galaxies blaze with the brilliance of the Milky Way or Andromeda. Some lurk in the shadows, so faint they're barely more than whispers against the cosmic backdrop. These are the dark galaxies, cosmic phantoms that failed to ignite with stellar light or had their stars stripped away by gravitational theft. Unlike their luminous cousins, dark galaxies are dominated by clouds of gas and dark matter, their sparse starlight drowned out by the void. Yet hidden within their shadowy embrace could be the origins of countless orphaned stars, ejected not by violence, but by the slow, silent unraveling of a galaxy that never truly shone. Take the infamous Dragonfly 44, a galaxy in the Coma cluster with the mass of the Milky Way but only 1% of its stars. This ghostly giant is so dim it was overlooked for decades, its existence revealed only through the gravitational tug it exerts on surrounding objects. Most of its stars didn't form in the first place, snuffed out by some primordial quirk of density or chemistry, but those that did, they're prime candidates for exile. Without enough stellar neighbors to stabilize their orbits, even a slight nudge from a passing galaxy or a ripple in dark matter could send them drifting into the abyss. Then there are the victims of tidal stripping, galaxies caught in the gravitational maw of larger neighbors. The Antlion II dwarf galaxy, for instance, orbits the Milky Way like a living fossil, its stars so sparsely scattered they barely register against the night sky. Over eons, the Milky Way's tides have siphoned away its stars, scattering them into the galactic halo or flinging them into intergalactic space. These aren't hypervelocity ejections, they're slow-motion abandonments, stars peeled away layer by layer like fruit rotting on the vine. The result, a trail of orphans with no home to return to, their parent galaxy reduced to a skeletal remnant. The darkest enigmas are the so-called ultra-diffuse galaxies, cosmic mysteries like NGC 1052 DF2, which appears to harbor almost no dark matter at all. Without dark matter's gravitational glue, these fragile systems are prone to disintegration, their stars vulnerable to even the gentlest cosmic breezes. A passing galaxy cluster or the tug of a nearby filament could scatter their stars like dust in the wind, creating a diffuse cloud of orphans with no central galaxy to claim them. What makes these dark galaxies so crucial to the story of orphaned stars isn't just their role as ejection sites, it's the clues they carry. Their stars often bear the chemical signatures of extreme environments, low metallicity, primordial gases, or odd isotopic ratios hinting at formation in near-vacuum conditions. By studying these exiles, astronomers can reconstruct the life and death of galaxies too faint to see directly, turning stellar orphans into forensic evidence of the universe's hidden structures. Yet the most haunting possibility is that dark galaxies aren't just contributors to the orphan population, they might be their final resting places. Stars ejected from luminous galaxies could, over billions of years, be captured by the weak gravity of a dark galaxy, becoming part of its shadowy ensemble. It's a cosmic irony. Stars cast away from the light might end their journeys in the darkest corners of all, their faint glow a testament to the universe's relentless recycling of matter and meaning. Isolated in the void, untouched by the churning chaos of galaxies, orphaned stars become something extraordinary: cosmic time capsules. Unlike their counterparts in bustling galactic neighborhoods, these stellar exiles aren't bombarded by supernova debris or tangled in the gravitational dance of neighboring stars. Their atmospheres remain pristine, their compositions locked in stasis, preserving elemental fingerprints from the era of their birth. For astronomers, these wanderers are more than just castaways. They're celestial archaeologists, offering a direct line to the universe's earliest chapters. Take the rare class of stars known as ultra-metal poor stars. These ancient relics contain vanishingly small amounts of elements heavier than hydrogen and helium traces, so faint they're like finding a single grain of sand in an ocean. In galaxies, such stars are nearly impossible to spot. Later generations of supernova have polluted their environments with heavier elements, masking their primordial origins. But orphaned stars, adrift in the intergalactic void, often carry these unspoiled signatures. Their composition matches theoretical models of the universe's first stars, massive, short-lived giants that forged the initial heavy elements in their cores before exploding and seeding the cosmos with the building blocks of everything to come. One of the most famous examples is He01075 5240, a star so metal-poor it's considered a living fossil. Discovered floating on the outskirts of the Milky Way's halo, its chemical makeup suggests it formed from gas barely touched by prior stellar generations. Had it remained in a denser galactic environment, its atmosphere would have been contaminated by later supernova. Instead, its isolation acted as a preservative, keeping its chemistry frozen in time like a prehistoric insect trapped in amber. But the time capsule quality of orphan stars isn't just about what they lack, it's also about what they carry. Some exiles contain unexpected abundances of rare isotopes, elements forged in environments so extreme they shouldn't exist in modern stars. For instance, a handful of hypervelocity stars ejected from the Milky Way's core show elevated levels of elements like europium and platinum, traces of the violent conditions near supermassive black holes. These stars are like cosmic canaries, carrying chemical evidence of events too distant or too ancient to observe directly. The preservation isn't perfect, of course. Even in the void, subtle processes can alter a star's composition over eons. The slow accumulation of intergalactic gas, the occasional encounter with a rogue planet or dark matter clump, these interactions leave faint marks. Yet these imperfections are part of the story, too. By studying how orphan stars deviate from ideal time capsules, astronomers can map the otherwise invisible structure of the intergalactic medium, tracing the faint currents of gas and dark matter that weave through the cosmos. What makes these stellar relics so invaluable is their ability to ground theoretical models in observable reality. Simulations of the early universe predict the existence of stars with specific compositions, but finding them in galaxies is like searching for a needle in a haystack. Orphaned stars, by contrast, offer a cleaner sample, their isolation acting as a natural filter against contamination. They're the control group in the grand experiment of cosmic evolution, providing benchmarks against which more complex environments can be measured. The hunt for these cosmic time capsules is accelerating. Next-generation telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope are poised to uncover even more pristine orphans, their advanced spectrographs capable of detecting the faintest chemical signatures. Each discovery adds another piece to the puzzle, helping astronomers reconstruct the universe's chemical evolution with ever greater precision. And as the catalogue of orphaned stars grows, so too does our understanding of how the cosmos transformed from a sea of hydrogen and helium into the rich, element-filled universe we know today. These stellar outcasts remind us that sometimes the most profound truths aren't found in the crowded centers of galaxies, but in the quiet, forgotten corners of the void. Their light, traveling across billions of years, carries messages from a time when the universe was young, messages that, thanks to their isolation, remain uncorrupted and clear. In their solitude, they've become the universe's archivists, safeguarding secrets that would otherwise be lost to time. Imagine discovering a planet orbiting an orphaned star, a world untouched by any galaxy's light, bathed only in the feeble glow of its exiled sun. The temptation to visit would be overwhelming, a chance to explore a place truly unlike any other. But should we? The ethics of interstellar exploration aren't just about capability, they're about responsibility. A planet adrift in the void might be the ultimate pristine environment, its chemistry frozen in time, its geology unscarred by asteroid impacts or cosmic rays. Landing probes or even human settlers could introduce contamination, not just biological but chemical or even gravitational, if our presence disrupts delicate orbital balances. We've seen how easily Earth's ecosystems suffer from invasive species. What if our curiosity inadvertently destroyed something irreplaceable? Yet the argument for exploration is equally compelling. Orphaned worlds could hold clues to the universe's deepest mysteries: primordial amino acids, exotic crystal formations, or even signs of life that evolved in total isolation. Their very loneliness makes them scientific treasures, offering insights impossible to glean from planets bathed in galactic radiation or crowded stellar neighborhoods. And if life does exist there, it might be unlike anything we've encountered, a shadow biosphere thriving in perpetual twilight. Ignoring such a discovery would be a rejection of humanity's deepest instinct: to learn, to understand, to push boundaries. Then there's the question of ownership. If no galaxy claims these stars, who does? International space treaties forbid nations from claiming celestial bodies. But orphaned worlds exist beyond traditional jurisdictions, in a legal gray area as vast as the void itself. Would exploiting their resources, mining frozen gases, or harvesting rare isotopes constitute exploitation or survival? For a civilization stretching beyond its home system, these lonely planets could be way stations, offering raw materials for generation ships or refuge from galactic disasters. But stripping them for parts without regard for their intrinsic value risks repeating Earth's history of colonial extraction on a cosmic scale. The dilemma forces us to confront what kind of interstellar species we want to be. Are we conquerors, spreading outward with little regard for what we alter, or stewards, approaching each new world with humility and restraint? The answer might lie in a middle path, sending observatories instead of landers, studying from a distance until we're certain our presence won't erase the very wonders we seek. After all, some places in the universe might be meant to remain untouched, their solitude a testament to the infinite variety of existence. Perhaps the greatest lesson orphaned stars offer isn't about them, but about us. Their light, traveling for eons through emptiness, reminds us that exploration isn't just about reaching new places, it's about recognizing our place in the grand tapestry. Before we set foot on a world without a galaxy, we'd need to ask not just whether we can, but whether we should. And in that question lies the difference between being wanderers and wise travelers in the cosmos. Among the countless orphaned stars drifting through the void, a handful defy conventional explanation, their trajectories too erratic, their compositions too anomalous to fit known models of galactic ejection. These cosmic misfits have led some theorists to a radical question: could these outliers be visitors from beyond our universe? The idea treads into the realm of multiverse theory, where our cosmos is just one bubble in an infinite froth of parallel realities. If other universes exist each with their own physical laws, and constant collisions or gravitational leaks between them might leave traces in our own. Orphan stars, untethered from known galactic structures, could be the perfect candidates for such interstellar interlopers. Consider the peculiar case of HD 140,283, nicknamed the Methuselah star. This ancient wanderer, drifting through the Milky Way's halo, has an estimated age older than the universe itself, a paradox that forces physicists to reconsider measurement errors or the star's unique history. But what if its extreme age and isolation hint at an origin outside our cosmic bubble? In certain multiverse models, adjacent universes might have formed microseconds earlier or later than ours, their stars bearing subtly different elemental signatures. A star ejected during a fleeting intersection between universes could carry these fingerprints, its chemistry and motion betraying its extra-dimensional roots. The mechanics of such cross-universe travel hinge on speculative but mathematically plausible phenomena. Brain cosmology, for instance, suggests our universe is a three-dimensional membrane floating in a higher dimensional bulk. When two brains collide or graze each other, immense energy transfers could eject matter from one reality to another. An orphaned star arriving via this cosmic backdoor might exhibit bizarre properties, unusual ratios of dark matter to visible matter, or isotopic abundances impossible under our universe's nucleosynthesis rules. Even its velocity could be a giveaway. A star propelled by interbrain forces might move in ways that defy local gravitational fields, like a swimmer against the tide. Critics argue that such theories stretch Occam's razor to the breaking point. Why invoke other universes when galactic dynamics can explain most orphans? Yet proponents counter that science advances by investigating anomalies, not dismissing them. The Gaia spacecraft's precise astrometric data has already flagged stars with impossible kinematics objects moving perpendicular to the Milky Way's disk or with velocities exceeding theoretical ejection limits. While most will have mundane explanations, even a single outlier resisting all standard models could revolutionize our understanding of reality. The search for multiversal orphans isn't purely theoretical. Next-generation telescopes like the Vera Rubin Observatory will map billions of stars with unprecedented precision, potentially identifying candidates worthy of spectroscopic deep dives. Key markers might include stars with deuterium levels inconsistent with Big Bang nucleosynthesis predictions, exotic particle signatures in their stellar winds, orbital trajectories that intersect regions where cosmic microwave background anomalies suggest past brain collisions. Ultimately, the quest bridges cutting-edge astrophysics and philosophy. If orphaned stars can indeed be messengers from other universes, their isolation takes on new meaning. They're not just castaways but cosmic diplomats carrying secrets from realms beyond our own. Whether these ideas withstand scrutiny or not, they underscore a profound truth. The loneliest stars in our universe might hold the keys to its grandest mysteries. For all we've uncovered about orphaned stars, the cosmos guards its secrets fiercely. These solitary wanderers still pose riddles that stump even the most brilliant astrophysicists. Take their sheer numbers. Current estimates suggest billions might drift between galaxies, but that's like guessing the grains of sand on a beach by studying a single handful. Telescopes spot only the brightest exiles, leaving the true population shrouded in uncertainty. Are faint red dwarfs the silent majority, outnumbering visible orphans 100 to 1? Or do we live in a universe where stellar exile is rarer than we think? Each new deep field survey reveals surprises. from unexpected clusters of orphans to vast, starless voids where theory predicted wanderers should roam. Then there's the enigma of their origins. While black hole slingshots and galactic collisions explain many hypervelocity stars, some orphans move too slowly for these violent scenarios. Their gentle trajectories hint at quieter ejection mechanisms, perhaps dark matter interactions or the gradual unraveling of fragile dwarf galaxies. Even stranger are stars found far from any known galaxy, with no visible path linking them to a parent system. Did they form alone in the void, condensing from rogue gas clouds in intergalactic space? Or are they remnants of galaxies so thoroughly devoured that no trace of their birthplace remains? These cosmic cold cases challenge our understanding of how stars live and die beyond galactic borders. The greatest mystery might be what these stars carry with them. Could some harbor exotic forms of matter unseen in galactic environments? Theorists speculate that the extreme isolation of intergalactic space might allow strange quark matter, an ultra-dense state where protons and neutrons dissolve into their fundamental components, to persist in stellar cores. Others propose that orphaned stars could accumulate mirror matter, a hypothetical substance interacting only through gravity, forming invisible halos around them. These ideas aren't just speculative, subtle anomalies in the way certain orphans move suggest they might be heavier than their light reveals, as if dragging hidden cargo through the void. Perhaps the most tantalizing puzzle is whether orphaned stars could rewrite the rules of physics itself. A handful of hypervelocity stars move slightly faster than our best models predict, their acceleration defying conventional black hole dynamics. Could this hint at unknown gravitational effects, or does dark energy, which drives the universe's expansion, interact differently with stars untethered from galaxies? Every anomaly, every outlier in the data is a potential thread leading to deeper truths about the nature of gravity, the distribution of dark matter, or even the possibility of extra dimensions subtly warping stellar motions. What keeps astronomers awake at night isn't just what we don't know, it's what we might be missing entirely. Current telescopes can't detect the faintest orphans, nor track their full journeys across cosmic time. Future observatories like the Nancy Grace Roman Space Telescope promise to unveil these shadows, but for now, the void keeps its secrets close. Each unanswered question is an invitation to look deeper, think differently, and remember that in the vast theater of the cosmos, even the loneliest stars have roles we've yet to understand. Galactic Orphans are the universe's silent witnesses, their solitary journeys carrying echoes of cosmic collisions, violent ejections, and the slow unraveling of galaxies over billions of years. These stellar outcasts aren't just anomalies, they're vital pieces of a grander puzzle, revealing how gravity sculpts the cosmos and how even the most seemingly stable systems are anything but permanent. Take hypervelocity stars streaking through space like celestial bullets. Their blistering speeds tell tales of close encounters with supermassive black holes, while their trajectories map the invisible influence of dark matter. Then there are the quieter exiles, red dwarfs drifting in the void, their faint glow persisting long after their home galaxies have merged or faded. These stars are more than wanderers, they're archives preserving the chemical fingerprints of their birthplaces like cosmic time capsules. But the story doesn't end with stars. Rogue planets untethered from any sun add another layer of mystery. Some may have been flung into the darkness during the chaotic infancy of their solar systems, while others were orphaned when their host stars were ripped away by galactic tides. Imagine a world where the sky holds no sunrises, no constellations, just an endless black expanse punctuated by the faint smudges of distant galaxies. Yet even here, in the coldest reaches of space, there's potential for the unexpected. subsurface oceans heated by geothermal energy or radioactive decay could harbor life in defiance of all odds. These frozen nomads challenge our definitions of habitability, proving that life might thrive in places we once thought barren. The study of galactic orphans is far from academic curiosity. Each discovery refines our understanding of galaxy formation, dark matter distribution, and even the ultimate fate of the cosmos. When astronomers trace the paths of these wanderers, they're reconstructing the history of galactic collisions, the growth of supermassive black holes, and the subtle tug of war between gravity and dark energy. The loneliest stars, it turns out, are some of the universe's most eloquent teachers. Their light, untarnished by the crowded environments of galaxies, offers a clarity that's hard to find elsewhere. Yet for all we've learned, these stellar drifters are a reminder of how much remains unknown. Every new telescope, every deeper survey, reveals orphans that defy expectations, stars moving too fast, planets orbiting too far, or chemical compositions too strange to explain. These outliers hint at physics we've yet to uncover, or perhaps even phenomena beyond our current understanding of the universe. The darkness between galaxies isn't empty. It's a frontier teeming with secrets waiting to be unraveled. So the next time you gaze at the night sky, remember, beyond the familiar constellations and the glow of the Milky Way, there are countless solitary travelers adrift in the void. Their stories are written in motion, in light, in the subtle whispers of gravity. They remind us that the universe is both violent and beautiful, chaotic and precise, vast beyond comprehension yet intimately connected. And as long as stars continue to wander, we'll keep searching, because every orphaned light in the darkness has a